intro to why reactions occur and how the energy change takes place. Chemical reactions always involve a change in energy. Change in energy. There is going to be some kind of slight change. Some of it is more dramatic than others where it gets really warm or it gets really cold and it's very obvious. But sometimes it's not that obvious. There is always an exchange of energy, though, for every reaction. Energy is neither created nor destroyed. You know this from the law of conservation of energy. It transfers forms. And for our purposes, for chemistry, we're really looking at the energy transfer to go from energy being stored in the bonds of the reactants being shuffled around into the bonds of the products. And yes, when the bonds break and the bonds form, you have an exchange of heat, heat being the thermal energy. So whether or not it's absorbing it from the surroundings or releasing it to the surroundings as to whether it would be endothermic or exothermic. Energy is absorbed or released. So the absorbed ones, where it pulls energy in from the surroundings, is called endothermic. Absorbed goes with endothermic. And released goes with exothermic, where it gives off energy, feels pretty warm to us. Just to review, we did talk about these back in Unit 1 briefly. Endothermic, chemical reactions in which energy is absorbed. Energy is required for the chemical reaction to occur. And the system gets colder. So, when we touch it, the system is pulling in energy. So when we touch it, it's pulling energy from our hand. That's why it would feel cold to us. Because energy always goes from the hotter source to the colder source. So if you're touching something that's cold, it's because it's taking energy from your hand. And these reactions would feel cold to us. Like if you put two solutions together and all of a sudden in the flask started to feel cold, you would know it's an endothermic reaction. The other way to know it's an endothermic reaction is, say, the copper 2 chloride one that we did in the lab, you had to actually heat it up. Like it was sitting there, it was this mint green powder, it wasn't doing anything, but when we started heating it, we gave it energy, then it started giving off gas. You did the flame test and realized it would extinguish, and it was CO2, but also you saw that turned into the copper oxide, that black powdery solid as well. But that case, we actually had to provide it energy in order for it to occur. And that's usually typical of most decomposition reactions anyways. One thing to note about endothermic is where to put the heat. The heat is always on the reactant side, okay? And it could also be written, instead of heat, it could just say energy. So if they have the word, the reactants plus energy, it's talking about an endothermic reaction. So you'll see that next to the reactants before the arrow there. For our exothermic side, exothermic, chemical reactions in which energy is released. Energy is released. It was originally stored in the chemical bonds of the reactants. There was more chemical energy in the reactants bonds than there is in the products bonds. So that exchange in energy, some of it has to go somewhere, so it goes into the surroundings, and we feel it as warmth or heat. So we're going to touch it and it's going to feel warm when it is an exothermic reaction. As you did with the zinc and the hydrochloric acid particular reaction, you touch the bottom of the test tube, it would have felt very warm or even kind of hot. So that one was a pretty vigorous reaction. But the bonds of the breaking of the reactants and the forming of the products, some of the extra energy that wasn't needed in the bonds of the products went somewhere, it went into the surroundings, and that's what we felt. Now, for the reaction, when you're writing out the balanced reaction, where does it go? It goes on the product side, it's being released. So also you could see it with the word energy in there. So if you see, reactants give you a product and then you see plus energy, you should identify it immediately as being exothermic. Now for our potential energy diagrams. You might want some colors out to go ahead and label these. I'm going to start with the endothermic one over on the left. This is the potential energy diagram for endothermic reactions. So these are called potential energy diagrams. And I'm going to label potential energy as just PE, so it's going to be shortened. On the endothermic side here, we have our axes, our y-axis, we have our x-axis. Over here on the y, the measurement will be in some form of heat unit. In this particular case, this one is showing the potential energy in kilojoules. You might see also other energy units such as calories or kilocalories as well, or joules, regular joules. On the x-axis, we're just showing the reaction progression. RxN is used to abbreviate the word reaction. Now for our actual curve. It starts out as this flat line over here, and then it goes and it makes this hill, and then it comes to another flat line over here. Potential energy diagrams are always going to have the two flat lines in the hill. That's how they're going to look. Over here on the left, the first flat line, this is the potential energy of the reactants. Okay? Over here on the right, this is the potential energy of the products. And those are actual measured values. You'll see on an example where they, on the y-axis, they give you the numerical value of the heat. Now, a couple other things to note here. Important thing. The activation energy, EA, is the activation energy. We're going to talk about exactly what that means in a little bit. Show you information about the activation energy. On the graph, though, the activation energy goes from the reactant line right here to the top of the hill. That is where your activation energy measurement is going to come from. Now, another thing to note here, this all the way down to the bottom here, this is known as the energy of the activated complex. The activated complex is a transition state, and in that hill part where the activated complex, the top of the hill, in that particular part of the graph, this is where the bonds are breaking, the bonds are forming. You have intermediate compounds that are very unstable rearranging. So that's why it has this big hill there. It's big rearranging of the bonds breaking and forming to get to your new products. The last thing that we need to note on our graph is something called delta H. Delta H is known as the heat of reaction, or the enthalpy of reaction. Now the delta H is always going to be from the product line to the reactant line. This amount here is our delta H. And what you're going to notice here is there's a way to calculate the delta H. Delta H is calculated by taking the heat of the products minus the heat of the reactants. So I would take this value right here and I'd measure it, and then I'd subtract the reactant line from it to get my change in heat. On the endothermic reaction, the product line is always higher than the reactant line. So our delta H always ends up being positive. Because the products are higher, when you subtract, you always get a value greater than 0. So take a moment to take a look at that before I go into the exothermic graph. Now let's look at the exothermic side. This is the exothermic one over here. There's only slight differences here on the exothermic graph. Let's draw in our Y and our X. Here's still the reaction progress. Here is still the potential energy in kilojoules. What you'll notice though is the reactant line is much higher. It forms the hill still, and then goes down a bunch down here to the product line. So our first line over here on the left is still the potential energy of our reactants. The line over to the right is still the potential energy of the products. The difference between the products and reactants is still delta H, but what you should notice here is that the product line is lower. So when you subtract the reactants from the products, your delta H is going to come out negative. And it should, because negative delta H's always indicate an exothermic reaction. The last little thing to note, the activated complex is the same. It's from the top of the hill all the way down. That's still the activated complex, PE of the activated complex. That doesn't change. The only other slight difference is the measure of the activation energy. If you look at the exothermic graph, the activation energy is a lot smaller because the reactant line is a lot higher than it is on the endothermic graph. So it doesn't take as much energy to get an exothermic reactions started. And if you're thinking about the magnesium one, yes, we did put it in the flame, we did give it heat, but it really was more of a catalyst than it was actually giving it additional energy. All it needed was that extra little spark to get started. And once it got the spark, the magnesium did the bright white light and gave off a lot of heat. Okay? So in that particular case, magnesium is highly flammable, so always keep it away from any kind of heat source because all it needs is a little spark and it ignites, just like alcohol or other flammable things. Any questions on the diagrams so far? Good with the diagrams?
Try and copy it over.
Okay, so let's look at the definitions of the activation energy. There, it finally disappears. Yes, it makes the writing there. The activation energy is the minimum amount of energy in the reactants need to possess in order to change into product. So it's basically the amount needed to get the reaction started. Okay, and it's still this measurement from the reactant line to the top of the hill. That would be your activation energy. This is a endothermic graph because I know this is an endothermic graph. The product line is higher. The activation energy is much higher, so I can tell this one is an endothermic one. So the difference between the peak is the activated complex, and the energy of the reactants. That's what you want to subtract in order to figure out your activation energy. And then delta H again right here was from the product line to the reactant line. That's always going to be, here it's written as EP minus ER, which you could still write it as HP minus HR. What do you think the E stands for? Energy. Energy is, in this case, it's energy in the form of heat. So you always subtract the heat of the reactants from the heat of the products. That's why delta H will be positive for endothermic, and it will be negative for exothermic. So keep that in mind. There is definite sign change here because you're always subtracting the reactants from the products. So let's look at our practice problem on the notes here. We are given a potential energy diagram. They also state to us the reaction up here. Carbon monoxide plus nitrogen dioxide, giving us carbon dioxide and nitrogen monoxide. All right, so let's do what it tells us to. First things first, label the reactants, the products, and the activation energy in the graph. So where am I going to label my reactants? The first flat line on the left here. So all I'm going to do is put PER, abbreviate. Potential energy of the reactants. Where are my energy of my products? Over here on this side, yes, the potential energy of the products. Activation energy. So I kind of can do like a dotted line here across. So from here to the reactant line, that's going to be my activation energy. So far, so good. We labeled the graph. Moving on. What are the reactants in this reaction? CO plus NO2, right? Over here, reactants. Good. What are our products? CO2 plus NO. Very good. Over here, products. How much energy is contained in the reactants? Now I just go to my graph. Here's my reactant line. How much energy? 10 what though? Let's make sure we get the unit right. This time it's kilocalorie, right? Kcal is kilocalories. Kilocalories is actually like one of the capital C calories that you see on your food labels. 1 kilocalorie is the same as one of those calories, the capital C calories. Okay? How much energy is contained in the products? 20. Very good. 20 kilocalories. Don't know why I wrote that. That's weird. All right. 20 kilocalories. All right, so a couple more things to do. What is the activation energy in this reaction? So somebody give me an estimate up here as to where you think the top of the hill is. 37 is probably a good estimate. It's a little bit above the halfway point. So yes, I could go with 37. So we would do 37 minus what? 10, because we have to subtract it from the reactant line here, right? So that's going to give us about how much activation energy? 27 kilocalories. Calculate the change in enthalpy. So what do I look for to calculate my enthalpy change? Here is the products, which was how much? 20 minus the reactants, which is 10. So in this case, it's going to be 10 kilocalories. And it's a positive value. So what does that also tell me about my reaction? It is going to be endothermic. It's a positive delta H. The product line is higher, so I know this one is endothermic. Any questions on that? All right, so let's talk some collision theory now. Collision theory. No, we're not actually having cars collide, but we are having molecules and atoms and elements collide in order for our reaction to take place. So, the definition really here is this point of collision theory states that atoms, ions, and/or molecules must collide in order to react. That is the first thing. If they don't hit each other, there is no way it's going to react. They actually have to physically run into each other. First major point here. And really, in essence, only a small fraction of the collisions that the molecules and the atoms and the elements do actually results in a bond-breaking, bond-forming kind of situation. Only a very small amount do, and I'm going to tell you why in just a minute. So take a moment. Atoms, molecules, ions, they must collide in order to react. That's our first major point of the collision theory. No collision, no reaction. Okay, so let's look at the other factors. The reactants have to collide with each other with enough amount of energy. If they don't have that threshold of energy, it's called the activation energy, they will not react. Okay? Must have this threshold of energy, that activation energy amount. If they do not have that amount of energy when they collide, they just bounce right off each other and go the other direction. There is no bond breaking, there is no forming. Okay? Has to have enough energy to break the bonds and form new bonds. Second major point, the reactions have to hit in the right orientation. So if they don't hit the right side of the molecule, once again, they'll just bounce right back, go in another direction. Okay? So it has to hit certain side in order for the reaction to occur. So this first example in the diagram is showing you that they're moving too slowly. And if they are moving too slowly, it really means they don't have enough activation energy. So they just bounce right off and go the other direction. The second diagram here is showing you that the oxygen is facing the NO3 here. The carbon is the one that has to bond with the oxygen, so it's not facing the right way. Since the oxygen collides with the NO3, it ends up just bouncing off and no reaction takes place. But if you look at the last one here, it has enough energy, it's moving fast enough, and the carbon is facing inward to collide so that the carbon can come in contact with the oxygen there and form the carbon dioxide over here, and then it creates NO2 as your other product. So you have to have enough energy, you have to hit in the right direction, and then bonds will break and bonds will form. So the bond that had to break here was between the NO right here. The bond that had to form was between the carbon and the oxygen there. So now we're going to talk about rates of reactions and how to speed them up. So this is where we're going to see our lovely analogy of how to get a date for the dance. It's a really cute TED Ed video. So let's go ahead and watch that, and then we'll come back and discuss these. First factor that helps speed up the rate of a reaction is increasing the concentration. Now, in the video that you just saw, the TED Talk with the how to get a date for the dance, you can do one of two things to increase the molarity. Molarity is actually, we haven't really learned the term yet, but molarity is basically the number of particles in a given space. Okay, the number of particles in a given space. So if you're looking at this diagram up here, obviously the one on the right has more particles in the given space, so the one on the right here, this one would have a higher molarity. Okay? And when you have more particles, you can collide more. Now, like you said in the video, there's two ways to do it. You can increase the number of particles, or you can decrease the space. Like cutting the hallway in half was decreasing the space, or adding more people to the building was increasing the particles. Okay? So that was one way to change. Those are both ways to change molarity. More particles or less space, it increases, they're going to bump into each other more, and then you're going to maybe have a more effective collision where it actually results in a reaction. All right, so here's showing you different ones here. The 6 molar, you guys use 6 molar in your lab, which is a highly concentrated acid, has lots of particles dissolved in that, as opposed to a 1 molar hydrochloric solution. As you can see over time, the 6 molar, of course, reacted a whole lot faster, and you used the 6 molar in the zinc chloride reaction, and that's why it bubbled so fast and it got so hot, was because it was very concentrated. So it was very effective at colliding and reacting. The 1 molar didn't react as fast over time, and there was still some reactant going in this one over here in time 3. Increasing the temperature. If you increase temperature, you're increasing the kinetic energy of the molecules. They are moving faster. If they are moving faster, they're more likely to run into each other and have collisions. That's pretty easy to understand. Increasing surface area. This was the Students need to stop traveling in packs analogy. Okay, so if you have smaller particles, if it's in powder form versus just a solid chunk, obviously if it's in powder form, there's more particles and more surface area for the other particles to run into. Okay, more collisions, more exposed molecules or elements gives you more collisions. Adding a catalyst lowers the activation energy. Collisions are more efficient and it speeds up the chemical reaction. And it basically, like in biology, you guys remember this from last year, you had your enzymes. Enzymes are biological catalysts. And what did they do? They had like the lock and key one where they would help orient the molecules in the right position so they would be able to react better. Same idea here, it helps lower the activation energy, it gets the molecules oriented and so they can break bonds and form bonds a lot easier. On the graph though, this is what you need to note on your graph, that in the hill part gets lowered. So you need to draw this in showing the new red line is how the graph would look with a catalyst. The activation energy, of course, is a lot shorter. And it's a lot easier to overcome that threshold of the activation barrier. Okay? So on a PE diagram, a potential energy diagram, you'll be able to tell there's a catalyst present because it'll show you the other line where the hill gets lowered. Okay? Any questions on the ways to speed up a chemical reaction? Pretty easy stuff.